Dear students, today in this session we are going to discuss the refraction at a spherical surface from geometrical optics. Okay. Before going to study the refraction at a spherical surface, we should have the knowledge of certain terms that I have mentioned here. So then you should know what is a spherical surface and what are the types of spherical surfaces. Generally there are two types. One is concave and the other one is convex. And the spherical surface is nothing but it is a part of a sphere, okay, where it may be having either concave surface towards the incident ray or convex surface towards the incident ray. Both are possible. And these are the following terms which we are going to use in our further discussion. That is aperture, vertex or pole, center of curvature, radius of curvature and principal axis. Again, in our next slide, I am going to define all these terms. This is a spherical surface. Here I have shown both convex as well as concave. So this XY represents a convex spherical surface and this is the incident ray, and XY represents a concave spherical surface, and the horizontal line which is going to pass through this P point, that is pole, is known as a common principal axis. Each spherical surface has a principal focus F as well as the center of curvature C and the radius of curvature. In case of concave also, the P is the midpoint of this surface XY, C is the center of curvature and F is the principal focus. Okay, now let me define an aperture XY. In my previous slide, this XY is said to be an aperture whether the spherical surface may be a concave or a convex. So what do you mean by aperture? Aperture is nothing but it is a surface area which is available for reflection or refraction. Pole, next term is pole. Pole is represented by P. As I shown you here in the ray diagram, so this P, which is nothing but the midpoint of the spherical surface, is generally considered as a pole. Next we have a center of curvature. So again it can be defined as a center of curvature of a spherical surface is nothing but the center of the sphere of which the given spherical surface is going to form a part. So this XY is nothing but the area available for reflection. So this is its center of curvature. It means this spherical surface is going to form some sphere. So that's why this XY is not a complete sphere. It is a part of the spherical surface whose center is a C. So that's why it is known as a center of curvature. Radius of curvature is represented as capital R. The radius of curvature, it is also given by the spherical surface. It is the radius of the sphere of which the given spherical surface is going to form a part. So principal axis, as I told you earlier, it is the line which passes through the pole as well as the center of curvature of the spherical surface. So here this horizontal line in both the cases is going to pass through the pole as well as center of curvature. Hence it is known as the principal axis. Okay. So here I have shown a ray diagram of a refraction of light with respect to concave surface, because in our next discussion we are going to discuss the refraction with respect to a convex surface. So for simplicity, for your knowledge, okay, I have shown this ray diagram where you can see that O is a point object which is placed on a common principal axis, and C is the center of curvature and P is the pole, and this is a common principal axis which is going to pass through the center of curvature as well as the pole, and the surface MN is an aperture or can be considered as a spherical surface which will separate the two medii, and these two medii are both are transparent but are going to possess different refractive indices. So OM is an incident ray here and CR is nothing but the normal drawn to the spherical surface. Then the refracted ray, OR is going to drawn as a normal to the surface, where this is the refracted ray this refracted ray. When this refracted ray is produced backwards, it will meet the common principal axis at I, which is the position of the image. Okay. Before going to study the refraction with respect to spherical surfaces, we require certain sign conventions. So usually we are going to follow Cartesian sign conventions, which is going to be used widely in different books. Okay, as we all know that this horizontal line is considered as a common principal axis, and this is known as the pole or a vertex. So according to a sign convention, First we assume that the light, when it is traveling from one point to another point, or when a light is made to incident on a surface, always the incident light is assumed to travel from left to right. So this is the direction of the incident light, and the distances which are going to be measured in the direction of incident light are going to be considered as positive sign. So it means V, image distance, F, the focal length, and the radius of curvature, if they are measured in the direction of incident light, so it is going to be considered as a positive. If the distances are going to be measured in the direction opposite to the direction of incident light, that is object distance U, image distance V, focal length F, and the radius of curvature are going to be taken as negative. And the basic convention is all distances in case of refraction as well as reflection, the distances are going to be measured with respect to a reference point that is known as a pole. In certain cases we used to have the extended objects. So this here I have shown an extended object which is placed perpendicular to the common principal axis, and if I want to measure its height, if it is perpendicular to the common principal axis and it is going to be measured in an upward direction, then the height of the object or height of the image may be considered as positive. If the height is going to be measured in the downward direction perpendicular to the common principal axis, it is going to be considered as a negative. And finally, the angles which are going to be measured clockwise are taken to be negative, and the angles measured in counterclockwise are taken to be positive. It means with these sign conventions, we are going to discuss the refraction of light with respect to a spherical surface, and by considering these conventions we are going to draw the geometrical figure. Okay, now let us come to the main point of this session. So our aim is to derive an expression for refraction formula with respect to a spherical surface which is going to form a real image. So here this xy will denote a convex spherical surface, and a ray of light is made to incident on it from a point object placed on a common principal axis. After refraction, the refracted ray is going to meet the common principal axis, that is at a point I, which is where we are going to get the formation of a point image. And the following relations will show you the formula for refraction. You are not supposed to worry about this. So in the next slide, I am going to tell you how to derive an expression for these formulas. Okay, first let me describe the ray diagram which I have drawn here. Okay, so this horizontal line is nothing but a common principal axis. Okay, so for this horizontal line, it is going to pass through the pole of this spherical surface as well as the center of curvature here, right? So here I have considered a point object O which is placed on the common principal axis, and a ray of light is made to incident along OA. Okay, it is made to incident along OA. A is the point of incidence on the spherical surface, and theta 1 is nothing but the angle of incidence. In order to measure the angle of incidence, what I have done here, I have drawn a normal. So in case of spherical surface, if you want to draw a normal, so you should draw a line from the center of curvature passing through the point of incidence. So in this case, Cn is considered as a normal, hence the angle between the incident ray and the normal is going to be taken as a theta 1. So at a point A, the light will suffer a refraction, and the refracted ray finally travels along AI and meet the common principal axis at I. Suppose if a ray of light is made to incident along the principal axis, that is along OP, the light is made to incident along OP, gets refracted along the common principal axis without deviation, since it is a case where the light is made to incident along the normal. OP is also considered as normal to this spherical surface. So if the incident ray is made to incident along the normal, so in case of refraction, the refracted light travels also along the normal. So this is another refracted ray. So these two refracted rays are going to intersect at a point I, where they are going to form the image of a point object, which is also a point. So in order to derive the refraction formula, here I have considered some angles. So that is alpha, beta and gamma. So alpha is nothing but the angle made by the incident ray with respect to the common principal axis. Beta is the angle made by the refracted ray with respect to the common principal axis. And gamma is the angle made by the normal with respect to the common principal axis. Apart from this, one more thing I have done. I have drawn AM perpendicular to the common principal axis, whose distance is represented by small h. Now here the U will denote the distance of the object from the vertex or the pole, and V will denote the distance of the image from the vertex again. So this spherical surface XY is going to separate two medium, that is rarer medium as well as denser medium, which are going to have the refractive index mu1 and mu2 respectively. And this ray diagram is drawn by considering that the mu1 is always greater than mu2. Is it clear? So in this figure we have shown how a ray of light, when it is made to incident on a spherical surface, gets refracted, and finally how it is going to form the point image of a point object. Okay, dear students, please keep this ray diagram in your mind, okay, so that in the next slide we are going to derive the expression for refraction formula. Okay, now let me come to the point, that is derivation of this refraction formula. If you consider the triangles, we have two triangles here. One is OAC and ACI. So let me clear here. OAC is one triangle and ACI is another one triangle. So when I consider these two triangles, from these two triangles I can equate for theta 1 as well as a theta 2. Okay. So these two relation, theta 1 is equal to alpha plus gamma, theta 1 is equal to alpha plus gamma, and gamma is equal to theta 2 plus beta, which is going to be considered as equation 1. So this relation is written with respect to a geometrical theorem which states that an exterior angle is equal to sum of two opposite interior angles. And we all know the familiar Snell's law, that is, according to the Snell's law, I can write mu1 sin theta 1 is equal to mu2 sin theta 2. In case of paraxial rays, there is an assumption, if the incident rays are paraxial, so then theta 1 and theta 2 angles which are made with respect to the common principal axis, okay, or if they are very small, so then I can assume that sin theta 1 is nearly equal to theta 1. So therefore here in the next step I have written mu1 theta 1 is equal to mu2 theta 2, which I have taken it as equation 2. So from this I can equate for theta 2. So theta 2 is equal to mu1 divided by mu2 into theta 1. From equation 1 I know that theta 1 can be replaced by alpha plus gamma. So theta 1 is replaced here by alpha plus gamma. Now substituting this equation 3, this is considered as equation 3. Substituting this equation 3 in 1, and after simplification I will get the equation 4, where I have mu1 into alpha plus mu2 into beta is equal to mu2 minus mu1 into gamma. Is it clear? So if you substitute this equation 3 in 1 and doing some simple simplification, I can come to this particular step. Okay. Next, again if you see the figure, okay, so here I have the angles alpha, beta and gamma. So by considering the triangle OAM, I can find out the tan value of alpha. By considering the triangle AMI, I will get tan value of beta, and by considering the triangle AMC, I will get the tan value of gamma. The same is written here. So tan of alpha is nothing but h divided by u plus delta, and tan beta is equal to h divided by v minus delta, and tan gamma is equal to h divided by r minus delta, which is taken as equation 5. So what is this delta? I will show you. So this delta I have not shown here. So it is a small distance between P and M. Okay, because when I take the tan of alpha with respect to this angle AOM, so tan alpha is equal to opposite side divided by base. Opposite side is h divided by base is OM, where this OM can be written as a OP plus PM, where OP is nothing but U and PM is taken as a delta. And in reality, so this distance will be very small. In the same case, in a tan beta, h divided by v minus delta. Tan of this beta is equal to h divided by this total distance is v, but I just want mi. So therefore, mi can be written as a pi minus pm, where pi is v and pm is a delta. So therefore, v minus delta I am writing over here. Right. Similarly, the value of tan gamma can be obtained as h divided by r minus delta, which is equation 3. Again here using an approximation that tan alpha is equal to alpha, since alpha is very small, so I can take tan alpha is equal to alpha only, and the distance delta, as I told you, that it is very small, so therefore it can be neglected. By neglecting delta and taking tan alpha is equal to alpha, the equation 5 will now become alpha is equal to h divided by u, and beta is equal to h divided by v, and gamma is equal to h divided by r. So substituting this equation 6 in equation 4, okay, and after simplification we are going to get the equation 7, that is mu1 divided by u is equal mu1 divided by u plus mu2 divided by v is equal to mu2 minus mu1 divided by r. So this is what the relation I get it when I substitute this equation 6 in equation 4 here. Equation 4 is here. If I substitute here the value of alpha, beta and gamma, I am doing some simple simplifications and I am going to get the equation 7. So now I have to apply the sign conventions here. So mu1, mu2 are the refractive indices which are not going to have any convention. Okay, they are not going to have any sign associated with them. So the distances are going to have sign. Okay, so u, v and r are going to have positive or negative sign depending upon the sign convention. So here distance u, in my case distance u is the distance measured from pole to the object point. Okay, so the direction of light here considered as from left to right, but I am measuring the distance of the object from right to left. So therefore, according to sign convention, I must take negative sign associated with u. Right. So whereas the image distance v, so image distance v is measured again from pole to I, P to I, which is in the direction of incident light. Hence, I can take positive sign for image distance. So radius of curvature is nothing but the distance from P to C, from center of curvature to the pole, so or from pole to the center of curvature. So again it is measured in the direction of light. Hence, it is also going to be taken as positive. So u will become negative, v is positive and r is positive. So therefore I can write equation 7 as mu2 divided by v minus mu1 divided by u. Just I have shifted the position of u and v, since u is going to get a negative sign. So I can write it as mu2 minus mu1 divided by r. So in case usually in our discussion with respect to this ray diagram, the rarer medium is always going to be considered as an air. If I consider the medium 1 as air, then its refractive index mu1 will become equal to 1. And second medium is also optically transparent medium, which is having refractive index slightly greater than that of the rarer medium. Hence it is known as denser medium, whose refractive index is denoted as mu2. So since in our case I can take this mu2 as mu, because mu1 is equal to 1. The same thing is done here. So mu2 is replaced by mu and mu1 is replaced by 1. So therefore mu by v minus 1 by u is equal to, again mu2 is replaced by mu here and mu1 is replaced by 1. So mu minus 1 divided by r, which is known as the formula for refraction at a spherical surface. Is it clear, students? Okay. So in brief, I will let you know what we have done, how we have proved this refraction formula with respect to this ray diagram. In the beginning, what we have done, we have taken the value of theta 1 as well as the theta 2. So this theta 1 is found to be equal to sum of alpha plus gamma, right? And this gamma is equal to theta 2 plus beta by using geometrical theorem, that is exterior angle is equal to sum of two opposite interior angles, and this is the Snell's law which I have used. From that I will get an expression for theta 2, and substituting this theta 2 in equation 1, I will get equation 4. So in this equation 4 I have to get the values of alpha, beta and gamma. This is done here by taking tan values of alpha, beta and gamma, and by assuming tan alpha is equal to alpha and neglecting delta, I will get the value of alpha, beta, gamma as h by u, h by v and h by r. The same is substituted in equation 4 and I got this particular equation, and in the next step I have applied the sign convention. So only the sign associated with the u changes, so therefore remaining v and r are going to possess the same positive sign. So therefore the relation is written as mu2 by v minus mu1 by vu is equal to mu2 minus mu1 divided by r. By considering the first medium to be air and the second medium having certain refractive index mu, so mu2 is going to be replaced by mu and mu1 is going to be replaced by 1, and I will get finally the refraction formula for spherical surface as mu by v minus 1 by u is equal to mu minus 1 into r. R, the radius of curvature, u, the object distance, v, the image, mu, refractive index of second medium, and 1 is the refractive index of first medium. Okay, students, so you go through it once again, okay, and you draw these rays diagrams along with sign conventions in a plain paper so that you can understand the derivation in a better way. Thank you, students.